Okay, number one. So we have, in the diagram, we have triangle ADE, we have line segment VC, and it's parallel. Okay, so it says, why are the triangles similar? Why is the smaller triangle similar to the larger triangle? What do we think? Angle ABC? Angle D, good. So I could say angle ABC is congruent to angle D, and what's our reason? They are what type of angles? Corresponding, good. So these are corresponding angles, and we know that they are congruent when the lines are parallel, good. Okay, what else? So we need at least two angles to be congruent in order to be similar. What's another one?
BC and DE, parallel lines.
Yep, so if BC and DE are parallel lines, what other set of angles could we get from that? C and E. So I have to just label C with three letters. How can we label C? Okay. And is it for the same reason, different reason? Yeah.
We don't want to get it mixed up with like angle BCE, right?
Right. Are they, I guess my question is, are they corresponding angles?
No, they're supplementary.
These two angles?
Oh, I thought you were talking about like the top C and the bottom C. All right.
Okay.
C and E are corresponding.
These two are corresponding, so yes, they will be congruent. So I have two congruent angles. Is that enough to prove triangles similar? Yes, and the reason we could say that they are similar is because of which method? Angle, angle. Okay. One other angle we did not take that we could have taken is which one? Angle A, right? So you could have said angle A is congruent to itself by that reflexive property since those triangles are overlapping. Okay. So now we're going to connect the segment lengths. So we have AB is 6. We have AD. Keep in mind AD is this entire side. That's 10. We have AC is 9. And we have to find a value for AE, which is that entire side. So somebody give me a proportion that we could use to solve.
1.66.
I'm sorry?
1.66. I don't know. I totally guessed that one.
Okay. Proportion. So let's take, for instance, little triangle ABC. What's the side of little triangle ABC that we know? 6. What is the corresponding side to the big triangle ADE? To the big triangle would be what? 10, because it's on the same side, right? It's on the left-hand side. So I could say in this little triangle, 6 compared to 10. Both left sides, both full sides of the triangle. Okay, I'm going to make this a proportion by setting it equal to basically that same idea, but on the other side of the triangle. So I'm going to go to the right side, but the top, the small triangle on the right side, that's how big? 9, compared to the right side's big triangle, which is going to be X. So this is a proportion. I feel like we are a little weak with proportions. Give me an idea. A little bit, okay. Okay, so to solve this, we are going to do what? Cross multiply. Okay, so if I cross multiply these things, 6 times x, we have 6x. 9 times 10, we get 90. And how do you solve for x? Divide by 6. And so what does x turn out to be? X is 15. Now, that gets us the entire side, right? So that tells us how big all of AE is. It also wants us to find CE. So how do you find CE? This whole thing is 15, and I'm just looking for that part. How do you find that part? 15 minus 9, right? So if we subtract that out, we can say CE is equal to 6. Simple thing. Okay, bless you. So then it's saying, let's find the following ratios. Okay, and in their simplest forms and compare it. Says, what do you notice about AB over BD? So how big is AB? 6. How big is BD? 4. And if I were to reduce these, I could leave this as a fraction and say it's 3 over 2. I could give you a decimal and I could tell you it's about 1.5. Okay, go to AC. How big is AC? 9. How big is CE? And again, if I were to reduce these, I could give you a fraction and tell you it's 3 over 2, or I could tell you it's 1.5. What do you notice? They're equal. They are equal. They're the same proportions, right? Same proportions? Okay. So why should I know that they are the same proportions? What do we know about the triangles? They are similar. So if my triangles are similar, what should I know about the sides? They should be in proportion, and they are. We showed it with numbers. Are we okay with that? Going on to number 2. So number 2 is just basically more than one triangle put together. So we got a couple of different triangles that we can look at. And all of these lines are parallel. Like that's the huge part here that you want to keep in mind. Since these are parallel, we get a whole bunch of different proportions that we can make. So we have RS is 15. We have TZ is 25. I missed one. VW is 6. WZ is 15. And it says we have to find the lengths of the missing segments. So I'm going to call STX and I'm going to call UVY. Okay. And I would do this one at a time. I would probably take a look at my triangles and say, well, let's just take a look at this big triangle here. And then keep in mind we have this other little triangle that's within there. And now this problem becomes like the same thing that you just had up above, where now we can make proportions. You can do proportions in 2 different ways. On the video notes, we said you could do full sides with, and you're going to hear me say this a lot. You can do wholes with wholes. You can do parts with parts. You can't do wholes and parts. And I'll explain. Whole sides with whole sides is what we did up above. Okay, so if we look up above, the proportions that we made, it was a whole side of triangle ABC compared to a whole side of triangle ADE. Okay, we can compare parts with parts. So if I were to just look at this red triangle, do we see how the side of the red triangle, say for instance SZ, has 2 parts? Okay, I could make proportions out of those 2 parts. So we could say something like X over 25. But because I'm comparing parts, I got to do the same thing on this side. All right, so again, I have to compare parts with parts. The 2 parts then that we would have would be 6 and 15. So you can compare whole sides with whole sides, or you can compare parts with parts, and that happens when your lines are parallel. What you cannot do is compare whole sides with parts of sides. Okay. To solve, what would we do? Cross multiply, and if we solve, I'm hoping, did we find X was 10? Maybe, hopefully. Okay, so now I know that this is 10. We can do the same thing, but let's take a different triangle now. So we have a bigger triangle. And if I took the bigger triangle, I could still do parts with parts. It's just the parts are going to be different. So only looking in the blue triangle, okay, keep in mind what are the parts that I have. I have a part of 15. Its corresponding part's Y. So then the other part I would need would maybe be this whole length. How big is that whole length? 35? And I would need this whole length here. How much is that whole length? 21. So do you see how in the blue triangle what I have done is I've used this parallel line and I've split it up so that we have parts with parts. So by saying that, I could compare 15 and 35 to the other side's parts, which would be Y and 21. Okay. Doing so, if we cross multiply and solve, hopefully we're going to find Y is about 9. Bless you. Thank you. Now, on the video notes, we had also talked about a corollary and extension off of that theorem, where we said you could also do it a different way. Because these lines are parallel, a different way that you could make this proportion is by just comparing, let's say, for instance, 15 and 10 to y over 6. That's a different proportion that you could use. Also comparing parts, and that only works because those lines are parallel. Okay. Questions that I can answer. So we can make a bunch of different proportions. We just have to be consistent in the proportions that you're making. Okay, on the back then. So an application that we have for this is comparing heights of buildings, because I know that we do this all the time, where we look at the flag and we're like, well, if the flag is this tall, then I obviously can make a triangle and make proportions and figure out how tall the building is. You don't do that? I do. I don't. Okay, in the diagram, we have a large flagpole and it stands outside an office building. Marquis realized that when he looks up from the ground, 60 meters away from the flagpole, that the top of the flagpole and the top of the building line up perfectly. If the flagpole is 35 meters tall and he's 170 meters from the building, how tall is the building? So the goal of this problem is to realize that we have a small little triangle and then you have a bigger triangle going all the way to the building, all the way up to the height, all the way over back to where he's situated on the ground. So again, they're saying make some proportions. Could you give me a proportion that we could use? What is it? Well, we could do it that way. So if I compared 35 over 60, so notice what we're taking, the sides of the small triangle, and I'm comparing the vertical side to the horizontal side. Now I just have to go to the big triangle and do the same thing. So what's the vertical side of the big triangle? H. What's your horizontal side of the big triangle? 170. That's a good proportion. That works. Okay. Cross multiply and solve. So if we cross multiply, we're going to have 60h is equal to 5950. And then if we divide through, we should find h, it's about 99.17 feet. Anybody do a different proportion? Could we do a different proportion? Sure. So we compared small triangle to big triangle. What if I compared like bottom sides and then I did vertical sides? So for instance, if I said, how about 60 compared to 170? So I did bottom side of the blue compared to bottom side of the black. Now I'd have to set that equal to vertical side of the blue and vertical side of the black. Notice what happens if we go to solve this. So different proportion, but what happens? Same stuff, right? So 60 times h, I get 60h. 170 times 35, I get the same thing. So you have multiple ways to set these up, because when you cross multiply, you're going to get the same answer. Okay. Are they similar? What do we think? Yeah, sides are in proportion. And what else can we find? Angles, right? Okay, we got a reflexive angle here. What should I know about a flagpole, hopefully, in a building if everything is constructed nicely? They're parallel. So then couldn't I go through and again tell you that these angles have to be congruent and these guys over here are congruent because they're corresponding. So we can prove those triangles similar in a whole bunch of different ways. Okay, and then for some reason I wanted you to find the height of the building again for letter B, but we already did that up on top. And we know the building should be about 98 feet. Any questions? That I can answer. A whole bunch of different proportions on these. And I have seen a bunch as I was walking around. Final answer should be 1.5. Number one, check your work and see, did I get 1.5? If we did get 1.5, good. Tell me the proportion that you set up to use to solve to get 1.5. Trevor, what'd you do?
X plus 1.5.
So if we're looking at this, remember how we said like you can compare parts with parts and wholes with wholes, right? So you're basically comparing parts with parts. You're taking the big triangle and you're comparing the left side top part to the right side top part, and then on the bottom, the left side bottom part to the right side bottom part. That works. When you cross multiply, please be careful. I think I caught a couple of you guys. Make sure, and I will do this, you'll even see this on my answer key. Write this out so that you don't forget. You have to distribute. All right, sometimes we look at that and we just kind of do it fast and either forget to distribute or, I don't know, forget a part, something like that. If we continue to solve, this would get you 2.5x, and then when we multiply that through, we get 3.75. Okay, subtracting that over, you get 2.5x, and then when you divide through, that's where you're going to get x is 1.5. Okay. There were other proportions I saw out there. What is a different one that you set up and solved and you could use, but is different from this, but still get 1.5? So notice what we're doing here. Same idea, still comparing like the parts with parts. It's just we did the top part compared to the bottom part on the left side, and then top part compared to the bottom part on the right side. Good. Everybody do it different.
I did 5 through 7.5 x plus 1.5 over 2x plus 1.
Good. So what she did, remember we said you could compare wholes with wholes. She looked at this and said, well, there's two triangles. So 5 over the x plus 1.5, that's the small side of the red triangle, small side of the red triangle, right to left. Okay. And then she said, but I compare whole side, so 7.5 on the right-hand side, compared to the whole side, 2x plus 1.5, where she ended up. That works. Also an okay proportion, you will get the same answer. Are there questions on that? Okay. How about number 2? Number 2, we should be getting an answer of 12. Okay. Maybe a proportion you could use. How about 6 over 8 is equal to x over 16? And we could cross multiply from there and get x equaling 12. Okay. Letter B, we also get x equal 12. So again, you could do this multiple ways. I know that this whole side is 15. If this little part's 6, then that tell me that 9. So I could say maybe like 9 over 6 is equal to x over 8. That's comparing like parts with parts. Okay, and we can do this, keep in mind, because it's telling us that these are parallel. If it does not tell, that's like huge. If it doesn't tell you that these lines are parallel, then we can't do that whole parts with parts deal. Okay, and if you solve, you get x is 12. You could also compare and make a ratio by comparing whole sides. So you could say something like 9 over 15 is equal to x over, how could I represent that whole side on that triangle? What would I have to do with the x and the 8? Add them up, so it would be x plus 8. Just be careful, because a lot of people like to tell me that's x times 8. Different. Okay, on the bottom down here, again, our lines are parallel, so that allows us to do that parts with parts kind of comparison. So bx is 4ba, the whole, ooh, that was bad. Whole side is 5. By is 6, and we're looking for bc. So I could call that x if I wanted to. Okay. Give me a proportion that we could use.
4, 5.
Good. And if you solve, you could solve this immediately, and this would tell you that x is 7.5. And you're done. Probably good. Questions? So those arrows are telling us our lines are what? Parallel. So we have 2 variables. So my thought is we don't want to try and solve both of them at the same time, because if you have 2 variables, then you need how many equations to solve? 2. So that's no fun. So my thought would be, could I just look at part of the picture? For instance, if I'm looking at x, I only want to look at part of the picture. okay? I want to be able to make up a proportion that is only using X and numbers, not Y. Any thoughts? X and 15, okay, I like it. X compared to 15. And 30 and 26, good. Okay. So I'm basically eliminating that top line, like you can cover that up. Those lines are parallel, sides are in proportions, or the parts are in proportions. And if we cross multiply, so I'm going to have 26x and 15 times 30, we're going to get 4. Thank you. And then if I were to divide through by 26, we get a decimal. And what is that decimal? Sure. Okay, so now I know that this is about 17.3. Could I use that same idea to find y? Okay, so give me a proportion that we could use to find y.
Y and 16.
Okay, y in 16.5. Okay, so what else could we do then? Y over 16.5 is equal to, good. Okay, so we have 15y, and if we multiply the 26 and the 16.5, we get 429, good. And then if I divide through by 15, we're going to get a decimal. What does y equal? Good. Okay. Let's jump to 6. So number 6, we have a whole bunch of segments that are parallel. Let's go and label the picture with all of the information that they've given us. So we have AB is 20. We have CD is 8, FD is 12, and then we have this ratio of 1 to 3. And typically I would tell you, anytime you see a ratio, what do we do with it? We haven't done this in a while. Sometimes, yeah. Attach a variable. Do you remember like when we did the dividing segments, we would put like variables. So 1 to 3, I could say like 1x to 3x. Notice I have nothing about BF right now. They have told us we know the perimeter. Perimeter meaning on the outside, all the parts added up on the outside. Okay, so we have to figure out first off, how big is BF? Then I can go back and figure out the x's. Now, think back to our warm-up, think back to the beginning. If these lines are parallel, I should know that these sides are in the same proportion as these sides. They're in that same ratio. So they're saying that they're in a 1 to 3 ratio. So this should also be a 1 to 3 ratio. I'm going to call this y, for instance, just for right now. So if I know it's 1 to 3, let's just drop the x for a second. I know it's a 1 to 3 ratio. So I know that my missing side, that y that we're looking for, is also in that same ratio or same proportion. We can solve this, right? So if I cross multiply, I'm going to find y is how big? 4. And maybe you didn't need a proportion to do it. These numbers are maybe a little bit easier. Sometimes they're not. Okay, so this would be a way that you could use, a method that you could use to solve. So now I know that this side is 4. What are we going to do to find the value of x?
You add up all the sides.
Good. Okay, so x and 3x and 8 and 12 and 4 and 20. And I know that that should total our perimeter, right? 64. So then you said we could subtract it out. So right now, what I would probably do is combine our terms first. Okay, so total of 4x. 20 and 4 and 12 and 8, we get a total of 44. And then we said subtract it away from 40 from our perimeter from 64. And then to solve, divided by 4, we're going to find x is 5. So now if I go back and actually answer the question, because it says find AE and EC, I know AE is X or 5. I know EC is 3X or a total of 15. Kind of, sort of. Let's jump over. Let me tell you, if you want a good challenge problem, you're like, this stuff is awesome, I love it, I can't get enough, I want proportions every day, all day long. Number 8 and number 9, I will tell you, are very challenging questions. If you want to try those and come in and see me, we can work on those. All right, I'm going to skip them for now, but if you want a good challenge and see, do I really have this stuff? That's a really good challenge. Let's go to question number 10. So it's just worded a little different and maybe labeled a little different. I have a lot more X's to deal with. But notice that they're telling us the triangles are similar. So what is that going to mean about our sides? They're in proportion. So now I'm not using that concept of like the side splitter theorem. Now I don't have triangles that are overlapping. I just have plain old triangles that are similar, and I have to find their values. And I have to keep the corresponding sides in order. Okay, so in other words, what does 2 correspond with? X, and 2x corresponds with 3x. Okay, so give me a proportion that we could solve here. Okay, there's a lot of x's, don't panic. We are going to do a little higher algebra here for a second. What do we do when we solve? Still cross multiply. Okay, so let's do the easier. 2 times 3x, we get a total of 6x. X times 2x, what do we get? 2x squared. Good. When you multiply variables, remember, you're going to add exponents. Okay. From here, we could solve this a bunch of different ways. My thought is always try and get everything onto one side of the equation. Okay, you got an x squared, you got an x, get it onto one side. Dominic?
Divide by x.
I could divide by x. That's another method that we could do. Okay. Let me show you the pull everything over to one side just because I kind of want to review the next step that's going to come up with that. Okay, so again, multiple options. One would be divide by x. One is going to be pulling everything over onto one side of the equation. So we have this formula here. So we have 2x squared minus 6x. What do they have in common? An x? Anything else? A number. What's that number? 2. So I'm going to factor out the 2 and the x. And then I'm going to give myself a factor, and I'm going to say, okay, 2x times what gets me 2x squared? X. Good. Okay. 2x times what gets me negative 6x? Negative 3. Good. Okay. I know we haven't done this in a while, so some of this is a little rusty. What did we do from here? I want to solve for x. What would we do? Okay, so if I distribute, here's where everybody gets stuck. If I distribute, I go right back to the step where I started from. I want to keep going. Think about what this is saying. This is saying I have 2 numbers that when multiplied together, they equal 0. We already, okay, nope, we already did that step. That's okay. We already did that step. Think about what this is saying. I have 2 numbers that are multiplying together to equal 0. How do I get something to equal 0 when I'm multiplying? I have to multiply by 0. So that means at least one of these has to be 0, right? So at this point, what you would do, don't even have to distribute, just solve it. I'm just saying I want this guy to be 0. Or I want you to be 0. Because I know if these 2 together, when I multiply, have to be 0, well then one of them has to be 0. At least. Okay, so what does x have to be here if I solve? 0. What would x be here if I solved? Solve for x, get x by itself. What would I do with the 3? Add the 3, right? So if I add 3 to each side, what is x? x is 3. So we get 2 answers here, but I have a side of a value of x. Can I have a side that's a value of 0?
No.
Could I have a side that's a value of 3 times 0? No. So this guy I have to reject. That's not going to be my answer. This one here will be my answer. I can tell you x is going to be 3. Okay. I know we haven't done that algebra in a while. I know that made that a little bit more challenging. Could you at least follow along with that? Let's flip over to number 12. Actually, what I think I want to do is let's go to 13 and then we're going to come back to 12. Okay. So Katrina's boat has come untied and floated away on the lake. She is standing on the top of the cliff that is 35 feet above the water in the lake. And if she stands 10 feet from the edge of the cliff, she can visually align the top of the cliff with the water at the back of her boat, because that's what we do when our boat has left us. That's exactly what we do, okay? Her eye level is 5.5 feet above the ground. Approximately how far out from the cliff is Katrina's boat? So notice what they're asking us. They're saying, how far is her boat here to here? So we're saying, I need to find that distance. What do you think's got to be true? First off, I guess I should ask, do we see that we have formed triangles here? We have a little triangle, and then we have a great big triangle, yeah? Okie dokie. What do you think is probably true about those triangles? They're in proportion, right? They're similar. I could prove to you because these lines, hopefully she's standing vertically and hopefully this cliff is vertical. They're parallel. So we could go through and we could say that these angles are congruent and these angles are congruent. So my triangles are similar. So sides should be in proportion. So give me a proportion that we could use to solve. Equals?
Equals 35.
Good. And to solve?
5.5.
Okay. And then to get x, we're going to divide by 5.5. And that means her boat is how far away? Like 6 feet. Sounds good. So her boat is a pretty good distance away from her. That's why she's staring at it. I also dig the fact that her boat's square on one end. That's kind of fun. I guess that happens. I don't know. It looks kind of silly, but questions on that? Okay. I hope she's going to get her boat. It seems like she's just actually watching her boat go away. So it kind of sounds like she's not going to. Right? And if they're like 63 feet away from you and they're unmanned, she's going to get a ticket. Right? This problem here is really not that much more challenging from the other problem. It's just the units that they've given us. Okay, and they love to do this on the Regents exam where it's like, easy peasy problem, I can solve this, no problem, and then all of a sudden they give you these weird units that you have to be careful with. So Dennis, and this is obviously what we do with a leaky roof too, needs to fix a leaky roof on his house, but does not own a ladder. He thinks that a 25-foot ladder will be long enough to reach the roof, but needs to be sure before he spends the money to buy one. He could have just rented one. He chooses a point P on the ground, where he can visually align the roof of his car with the edge of the roof of his house. Dennis determines if, help Dennis determine if a 25-foot ladder will be long enough. Okay, silly problem. Nobody does that. They just rent the ladder or buy the ladder, and then if it doesn't fit, you return it, and then you move on. And then you rent a different one. Notice how they've given us this material, though, this information. 8 feet 6 inches. Please do not write that as 8.6. I know that that's what we want to do. How many inches are in a foot? 12. So what is that really representing? 8.5. Because if I have 6 inches in 1 foot, I have 12 inches total for 1 foot. So this is 8.5. Okay. The 4.3 3 inches. So 3 out of 12 is really what? Okay, so this here is really 4.25. That was the hardest part of the problem, is just making sure that you have the correct units. Okay, keep in mind we're trying to find, will that ladder reach the roof of this house? So give me a proportion now that we could make. Over 4.25, okay. Equals, now, can't do 23 over x. Can't do x over 23. What's the issue with the 23? It's not the whole. So remember in the beginning where I said parts of parts and wholes of wholes, but you can't do parts of wholes.
Yeah.
This is a part where x is a whole side of a triangle. So you could add. Okay, so I need this whole length here. How big is that whole length going to be? 31. 95. Okay, so now let's go again. So we had 8.5 over 4.25 is equal to and we can cross multiply and solve this. So we get 8.5x. If we do 31.5 times 4.25, what do we get? Okay. And then from here, divide by that 8.5, and we find x is, so if the house is about 15.75 feet tall, will a 25-foot ladder reach to the top of the house?
Yes.
Yes. So he is okay with buying that ladder. Thank goodness he lined his eyesight up with the heart to that problem. We are okay. You could.